The next set of material that we're going to look at is systems of equations. We'll get into what a system of equations is in a few minutes, but in order to do this section, you want to be able to determine if a point is a solution to an equation, understand how to graph a linear equation using the techniques from the previous chapter, and be able to identify the coordinates of a point in the rectangular coordinate system. Upon completing this presentation, you will be able to understand what a system of equations is, understand how to check if an ordered pair is a solution to a system of equations, and be able to solve a system of equations graphically. So what is a system of equations? A system of equations is a group of two or more linear equations. These will usually be in two variables. A solution to a system is an ordered pair that is a solution to all equations in the system. So we're going to be doing things that are going to be repetitive. Not only does it have to be a solution in one, it needs to be a solution in all of them. So the first thing that we're going to look at is determining if an ordered pair is a solution. So we've done this several times already. Remember that we looked at in Chapter 2 or in Module 2, we determined whether a number was a solution. And remember that a number was a solution if when you plugged it into both sides of an equation, it yielded a true statement. We also looked at whether a point was a solution to an equation by plugging in the values for x and y into an equation and determining if we got a true statement. In order to be a solution to a system, we're going to use our techniques from Module C, and we're just going to do this a couple times. We want to plug the coordinates of the point into each equation and determine if it is a solution to that equation. If it works in both or in general in all, then it is a solution to the system. So let's look at some examples of this. For our example, we have a system of equations. A system of equations is denoted by the squiggly brackets on the left, and basically this is saying that these are grouped together. We want to determine if our point for -1, if it is a solution to the system. Now, we've seen that when it comes to equations in two variables, there's an infinite number of solutions on each line. Now, when it comes to can it be a solution to the system, then that can be a little bit more refined. So, again, all we have to do is we're going to plug the coordinates of this point into both equations and check if it is a solution to both. So what we have here is we have x is 4 and y is -1. So in my first equation, we have x plus 2y equals 2. I'm going to plug in the numbers. So for x, I'm going to replace it with 4. For y, I'm going to replace it with -1. We still have, I want to know if this is equal to 2. We want to simplify both sides of our equation. So we get 4. 2 times -1 is -2 equals 2. 4 minus 2 is equal to 2, and is that equal to 2? Yes. So this one checks out. It is a solution to the first equation, but again, that's not enough in order to be a solution to the system. We need to check it in the second equation. So if we check it in the second equation, we're going to repeat the process. I want to plug in 4 for x, and I want to plug in -1 for y. And we want to simplify each side. So we get 4, -2 times -1 gives me +2. I want to know, is this equal to 6? 4 plus 2 is 6, which is equal to 6. So it is also a solution to the second equation. Since it is a solution for both, then 4 -1 is a solution to the system. And we're done. Okay, let's go ahead and look at example B. Example B, we're going to do the same thing. I want to know, is -4, 3 a solution to the system? So I'm going to plug in -4 for x since it's the x coordinate, and I'm going to plug in 3 for y since it's the y coordinate. So in my first equation, we have x plus 2y equals 2. I plug in -4 for x. I plug in 3 for y. And I want to know, is this equal to 2? If we simplify, we get -4. 2 times 3 is 6. And I want to know, is this equal to 2? -4 plus 6 is equal to 2. And since 2 is equal to 2, it is a solution to the first equation. So now the question comes about, is it a solution to the second equation? Well, if we plug this into our second equation, x minus 2y equals 6, we get -4, plug in for x, minus 2 times 3. I want to know, is this equal to 6? So if we simplify the left side, we get -4. -2 times 3 is minus 6. We get -4 minus 6 is -10. We have same signs, so we're going to add and keep the sign. And so our resulting, when we check this, we get -10 equals 6, and that is not a true statement. So -4, 3, is it a solution to the system? It is not. So the important thing is here to keep in mind that a point can work in one equation does not necessarily mean that it's going to work in both equations. And so you do need to make sure that when you are determining if it's a solution, you do need to make sure you keep in mind both equations. Remember that when we talked about determining if a number is a solution, we said that in terms of just being asked that question, it wasn't going to come up very much. When do we use determining if a number is a solution? We use it when we want to check our work. And so when we talk about determining if a point is a solution, it's going to be the same thing. This is going to be our check step when we start solving systems of equations. So we're going to talk about solving systems of equations graphically. This is mostly going to be review of graphing linear equations in two variables. So the first thing we want to do is we want to graph each line using whatever method you are most comfortable with. We want to graph them on the same set of axes. We want to make sure that we graph carefully and precisely. We want to find the point where the lines intersect. This is the solution. We're going to write the answer as a point in ordered pair form. Now, one thing I do want to point out is solving a system of equations graphically is generally done using technology, not by hand. The reason is that if you think about graphing by hand, you run into a lot of issues. One, if you draw sloppy graphs, are you really going to be able to figure out where your point of intersection is? So the thing is, when you do this by hand, it has to be very precise. And can you be as precise as your calculator or your computer? And the answer is no. The other reason is that what if your point of intersection is not a nice point? We're not going to look at any of those here, but it's entirely possible that your point of intersection involves fractions or decimals. And if you're graphing by hand, are you going to be able to accurately determine what your point of intersection is? And the answer is no. So this will be explored more in future math classes when you start using a graphing calculator, computer, etc. So why are we doing it here? The main reason is because I do want you to be able to see exactly what it is we're looking at. We're only going to look at a couple of examples, and this is not stuff that you will be quizzed on or tested on. We will be looking at other methods to solve systems of equations. So let's go ahead and look at an example. Again, when solving by graphing, if you are doing this by hand, it is encouraged that you use actual graph paper and that you try to make your graph paper as large as possible in order to get this to be as precise as possible. It's also recommended that you use a ruler to make sure that your lines are straight. So, our example that we have is we have 2x plus y equals 6 and 2x minus y equals negative 2. So the first thing we want to do is graph the first line. There's a couple different ways that you can do this. If you want, you can create tables, you can use intercepts, you can use slope-intercept form. So let's go ahead and do the first one. I prefer intercepts on this one. So I'm going to go ahead and create some tables. My green table, this is going to be 2x plus y equals 6. And I'm going to use intercepts, so I'm going to plug in 0 for x and 0 for y. If we plug in 0 for x, my x term goes away, and I am left with just y equals 6. So there is my y-intercept. If I plug in 0 for y, I get 2x plus 0 equals 6. My y term goes away, and if I divide by 2, I get x equals 3. So there are my 2 points for my green line. So let's go ahead and graph this. If we graph 0, 6, we want to go up 6. 1, 2, 3, 4, 5, 6. It's going to be right here at the top of my graph. And 3, 0 is going to be 3 to the right. 1, 2, 3. So now we can go ahead and draw our line through these points. And again, make sure that you draw this as carefully as possible. Mine is not fantastic, but I think I went through everything I needed to go through. And we have our first line. So now we want to go through our second line. Our second line, I'm going to do the same thing. I'm going to go ahead and create a table. And again, I'm going to go ahead and use x and y intercepts. So I want to plug in 0 for x and for y. So if we go ahead and do this, if I plug in 0 for x, I'm going to get 2 times 0 minus y equals -2. My x term cancels, and I need to divide by -1 to get y by itself. So we get y equals +2. If we plug in 0 for y, I get 2x minus 0 equals -2. My y term has canceled out, and so I need to divide by 2 in order to get x by itself. We get x is equal to -1. So now let's go ahead and plot these points. 0, 2 is my y-intercept. That means I want to go up 2. And so we're going to plot our point right here. -1, 0 is my x-intercept. I want to go 1 to the left and not go up or down. And then now we can go ahead and draw our line. And our picture should look like this. So now what are we looking for? We are looking for the point of intersection. The point of intersection is the point that lies on both lines. And so our point of intersection is where our green line and our blue line intersect. Our point of intersection is right here. And so now I need to figure out what are the coordinates of this point. So remember, to find the coordinates of the point, we want to start by moving left or right from the origin. In order to get to this point, I am 1 to the right of the origin. That is my x-coordinate. And my y-coordinate is 1, 2, 3, 4 up. And so my y-coordinate is 4. And my point of intersection is 1, 4. And that's what we're looking at when we are talking about solving a system of equations graphically. So when will we see this again? We will use this procedure for determining the first part. We will use determining if a point is a solution when we check our answers after solving a system of equations graphically. You will explore solving equations graphically, including systems of equations, more in your future math classes. In your future math classes, you will not only need to know the point of intersection in terms of solving systems of equations, but also solving inequalities. Systems of equations will be extremely important if you are going into any kind of business or science field. We are talking about equations with more than one variable or more than one unknown. And in real life situations, rarely do we see just one unknown. Upon completing this presentation, please answer the following questions as part of your notes. How confident are you with the material presented in this presentation? What from this presentation needs to be explained further? And how much more practice do you need to be comfortable with the topic.